Okay, so this is my last video on trig equations. So we're going to be looking at equations with multiple angles, and so I'm going to start with an example. Cosine of 2x equals sine x. So how would you know that this is multiple angles? So there's two real cues here. One, this is in terms of 2x and this is x, so that we don't like. And then also this is cosine, this is sine. So ideally what you want is you want to have everything in like the same terms. So either everything is in terms of 2x or everything is in terms of x, but 2x and x is no good. And then also the other thing that you would really like is the same trig function. So we have multiple issues here. So when this happens, what you're going to want to do is you're going to want to look at your equation, and you're going to really want to use identities. And in this case, we want to get this in terms of x alone, and also we'd really like this to be in terms of sine. So which identities will help us with that? Well, that would be the double angle identities, right? This is just screaming to use double angle identities. And more specifically, we want to use this identity here, which will transform that cosine of 2x into a function in totally in terms of sine. So I will make this replacement of cosine of 2x with this 1 minus sine squared x. All right, so now what do we do? Okay, so you probably want to bring everything over to one side, and ideally you probably want to factor it, right? So if you have been watching my videos, you can probably finish this one yourself. I would recommend pausing here and just getting caught up and then solving it, and then we'll go on from there. So to factor this, I've got my factorization here, like you see, and so then I can go ahead and I can set each factor equal to 0, and then I solve both factors for sine, and so then I have to just figure out where is sine equal to 1/2 or sine equal to -1, so I can refer to my unit circle, and so these would be the places where that all occurs. So my solutions in this case are pi over 6, 5 pi over 6, and 3 pi over 2, and so we're done. Okay, so that's kind of the idea. So let's take a look at another one of these. So I've got 2 cosine squared x minus 2 sine squared x plus 1 equals 0. Okay, so we've got a similar problem here. So these are both in terms of x, but this is cosine, this is sine. We don't like that. We prefer to have this all in terms of the same trig function. So you want to think about trig identities and just what is popping out at you. And the thing I want to emphasize in this video, this is not a perfect process. I cannot just tell you, boom, this is what you do every single time and it's going to work. So I want to walk you through kind of how I thought through this problem so that you can see that, I'm a seasoned math teacher, but I don't know how to do these right off the top of my head either. So I had to kind of get a little creative. So the first thing that came to mind was I saw cosine squared, sine squared. I thought Pythagorean identities, right? And so here's the thing. I thought sine squared, this one here, right? And okay, so here's the deal. We do not have sine squared plus cosine squared, right? We have cosine squared minus sine squared. So this is not quite what we have. We could maybe use this, but this is just going to create a bigger equation. And so perhaps this is not ideal. So we want to keep thinking, what other identities have cosine squared and sine squared in them? And then I thought, oh, the double angle identities. Now again, I just want to walk you through from the perspective of maybe I don't totally know what to do. So I have all these different ways I can think about my double angle identities. And what I'm going to do is, I've got 2 sine squared x in my equation. So what I could do is I could use this identity here, and I could manipulate it and then put this identity into my equation. So what would this become? Well, this would become, so notice that I've got 1, this is really 1 minus 2 sine x, right? 1 minus 2 sine x. So this whole thing here, so 1 minus 2 sine x becomes cosine 2x. Okay, so let's say that I made this switch here. Why is this not ideal? Well, you already know, right? So not ideal because now I have x and 2x, and we want to have the same terms here. So you want to do this kind of investigation. Like you're going to make a shot in the dark, and then you want to look at, the type of identities that you use, and then say, does it make sense? Is it ideal? And I can tell now by looking at this is not ideal, so I should try again. There's probably a better choice. So now what I'm going to do is I'm going to look at my equation, and I'm going to say, all right, well, I'm kind of stuck here, but these both have a 2. So let me factor the 2 out. And now, in looking at this newly factored out 2 version of the equation, cosine squared minus sine squared, well, check it out. With the double angle identities, that is what this is right here, right? And so this is kind of cool, actually, because check out what this does. Then I can replace this cosine squared x minus sine squared x. I can replace this with cosine 2x. And now I've actually gotten rid of both trig functions. I've introduced a new trig function, and now I'm good to go, right? So, all right, that's cool. So now I can solve for this. Now, there is a little bit of a plot twist. So let's go ahead and we solve for cosine of 2x. And so now I want to look for where cosine equals -1/2. So I refer to the unit circle. And so I have cosine is -1/2 here and here, so that's 120 and 240 degrees. Okay, so I have these 2 measures. But here's a weird thing that happens. We're not done. So I like to say not so fast. Before I continue on with this, I actually want to consider the solution set. So we found all of the solutions from pi equals 0, or pi is between 0 and 360. This is the mentality that we went in with. So we looked for all the values where theta was between 0 and 360. But this is not what we're looking for, right? We are actually looking for 2x, or 2 theta. So when I was looking at the unit circle, I wasn't thinking quite big enough. So what I want to do now is I want to expand this interval, and I want this to now be centered around 2 theta. So what I'm going to do is I'm going to multiply each part of this inequality by 2. So actually now what I want to do is I want to find more solutions, and I want to think about the unit circle going on to 720 degrees. And this will all make sense in a second. So from here to here, this is 360 degrees, right? So how do I get to 720 degrees? I just make one more round around the unit circle. So those 2 solutions that I found from earlier, now if I want to take those out to 720 degrees, I just add 360 to those solutions. And so now I actually have a whole set of solutions. So 120, 240, 480, and 600. So we've expanded this. Now, why did I have to do this with 2x when I didn't have to do this with 1/2 x? Because if you watch my other video, you might be thinking, well, I didn't worry about this with 1/2 x. So you don't have to worry about this with 1/2 x, because 1/2 x, you can figure that out within the confines of the singular unit circle. This only becomes a problem when this number here next to the x is going to be greater than 1. So that's why I had to worry about this here. Okay, so anyways, so I found these 4 solutions. This is now 2x equals each one of these things. And I have that proper interval. And now to finish solving for x, I can just divide each of these by 2. So my answer will be 60, 120 degrees, 240 degrees, and 300 degrees. And you might have been thinking when I was doing this, wait a sec, my interval was from 0 to 360 degrees. You're right. And look, after I divided by 2, that's actually what happened to my solutions, right? They all actually fell within this interval. So this is like a weird thing that you have to do when you have a number attached to the x greater than 1. You have to kind of consider this and worry about this. Now, what if I wanted to solve this equation now for all solutions? How would I do that? Okay, so remember, our original solution set was 60, 120, 240, and 300 degrees. So the way that I like to look at this, I always like to view this on the unit circle. And I just like to notice if there's like any patterns. So in this case, these 2 solutions are 180 degrees apart, as are these 2 solutions. So because these are 180 degrees apart, so you can start here, and then every time you go 180 degrees around the unit circle, you hit a solution, and same for 120. So the format of our solutions will be 60 plus 180 degrees n, and 120 plus 180 degrees n. Okay, so a little bit of a plot twist there, but now that you know this, you can kind of expect it. So now I've got cotangent of 2x minus cosecant 2x equals 1 from 0 to 2 pi. All right, so we're going to need to experiment here, and the thing that you want to realize is that there is no double angle identity for cotangent and cosecant. So I might say, oh, cotangent I see 2x, I want to use a double angle identity. I can't use those because I don't have one for cotangent or cosecant. So I am going to show you a little bit of a trick here, because this is something I think you probably wouldn't think of. And sometimes when you do problems like this is like one of those areas in math where like these are pretty hard sometimes, and there might be some tricks that you didn't know you could do. So right now what we're doing is we're kind of trying to add to your bag of tricks, if that makes sense. So here's the trick. I'm going to rewrite this where I want cotangent on one side and cosecant on the other side. And then I'm going to square both sides. Why? Okay, so let's just go with this for a moment. So let's go ahead and expand. So if I expand this, I get cotangent squared 2x equals 1 plus 2 cosecant 2x plus cosecant squared 2x. So you should do that on your own and just make sure that your math agrees with mine. Okay, so remember what we're trying to do. We're trying to solve this, and right now, where I started with this, I had this equation with cotangent and cosecant, and I had no way to really do anything with these. But now that I've squared everything, I've got cotangent squared and cosecant squared, and we do have an identity that deals with cotangent squared and cosecant squared. Namely, that's the Pythagorean identities. So I could actually use this little identity here. And the reason that helps me then is I can work towards getting my function all in terms of, you know, the one trig function. Okay, so what I'm going to do then is I'm going to take my cotangent, and now I'm going to rewrite it in terms of cosecant squared 2x minus 1. So check it out. Look at what happened. I squared both sides, which seemed really weird at the time. Why would I want to do that? But by doing that, that opened up the ability for me to use certain identities. And now I have everything in terms of the same trig function. And better yet, so I've got cosecant 2x and cosecant 2x here. So I can actually cancel those out. And so then I'm left with -1 equals 1 plus 2 cosecant 2x. And so this I can solve, right? This is actually a much easier thing to solve. So now I can go through and I can solve this. And so I get cosecant of 2x equals -1. So I need to just look for where I get -1, so that would be here. So then I can write out that 2x is equal to 3 pi over 2. But am I done? So you should be saying to yourself, wait a sec, this is 2x. Isn't this just like the last problem? You'd be right. So what I want to suggest to you now is I want you to go find the other solution. So what manipulations do you make to find that other solution? So pause here and try to make that argument to yourself, and then hit play when you think you've got it. Okay, so we said that we found this one solution. So I had this 2x equals 3 pi over 2. But remember, when we thought of this solution, this is when we're thinking of our x's just between 0. This is looking at x between 0 and 2 pi. And we don't have just x here, right? We have 2x. So what I actually want to do then is I want to think about expanding my unit circle to 4 pi. So if I go once around here, this is my solution for 2 pi. If I go another round, that's 4 pi. So what would this new solution be? I want basically the same solution here after I make one more rotation around the unit circle. Well, all I have to do is add 4 pi to this, and so this becomes a 7 pi over 2. And now I can say that I found the other solution. So I've got 2x equals 3 pi over 2 and 2x equals 7 pi over 2. So I can divide both sides by 2 now, both of these by 2, to get 3 pi over 4 and 7 pi over 4, and then those are my two solutions. Okay, so next I've got cosine of x minus 1 equals cosine of 2x, and I think you should try this one. I think you have enough in your bag of tricks to figure this one out on your own. You'll get more out of this if you try this on your own, so pause here, hit play when you think you've got it. Okay, so I've got cosine of 2x. This is just screaming for a double angle identity, right? So when I think about my double angle identities, I probably want to use this one so that I get everything in terms of cosine squared. So I replace my cosine of 2x with 2 cosine squared x minus 1. And now I want to bring everything to one side. Notice that the -1s will drop out, so I'm left with cosine x equals 2 cosine squared x. Okay, so one thing I want to mention here, do not divide by cosine. Why? So what you really want to do is factor. Basically what will happen if you divide by cosine is you end up canceling out one of the possible solutions. So never divide by the function that has the x in it. Don't divide out by the variable you're trying to solve for. Okay, so what you want to do is subtract off that cosine x, and then look what happens. I factor out that cosine, and this is what I mean. If you divided both sides by cosine x, you would lose this factor of cosine x, and this holds like a whole set of solutions, right? So you don't want to accidentally divide that out. So instead you want to factor it out, like you see here, and this leaves me with 2 cosine x minus 1. And now I can set each factor equal to 0, so setting each one equal to 0, and then I can go ahead and solve. So for cosine of x, so I know that like if I were on the unit circle, what I like to do when I have to figure out for all solutions is I just like to figure out the format of my solutions first, just in the unit circle. So I know that this would be from pi over 2, 3 pi over 2, etc. And then for the other equation, so when I look for where cosine of x equals 1/2, so that occurs when I have pi over 3, 5 pi over 3, etc. So first I just figure out on the general unit circle, where would my solutions be? And then I like to reference the unit circle, and I like to just highlight like where those solutions are and if they're 180 degrees apart, because then that helps me to write the solution set. So pi over 2 and 3 pi over 2, those are 180 degrees apart. 180 degrees apart, so I can just start at pi over 2 and then do plus I think I said 180, I should say pi, not 180, sorry. And then same, and then here, so there is no, like these are not 180 degrees or pi radians apart, so these are going to need separate solutions. So sorry, I wrote 180, I should have written pi. Anyways, so my solution set will be pi over 2 plus pi n, pi over 3 plus 2 pi n, and 5 pi over 3 plus 2 pi n. Okay, so here's another one for you. So again, I think that you should try this one. I think you know enough to handle this, and then you can hit play when you're ready. Okay, so in this case, I'm going to go ahead and I'm going to use sine of 2a equals 2 sine a cosine a. Okay, so I'm going to set this up as you see here. And now you might be thinking to yourself, okay, but I can't get everything in terms of one trig function. Okay, so here's the deal. You can't always get these to be in terms of one trig function. That's your ideal goal, but it's not going to happen with this one. So what we're going to have to do is we're going to deal with this as is, but we can still figure this out. So what I'm going to do is first I'm going to divide out the 2's, and then I'm going to subtract the sine x, cosine x to the other side, and I'm going to factor this. So if I factor this, this becomes cosine x times cosine x minus sine x. And so can I solve this? I actually can. So I can set both factors equal to 0 like I normally would. And so from here, so of course for cosine x, so we'll do this in terms of degrees. So I know that cosine x equals 0 at 90 and 270 degrees, etc. Now this one we can totally do. We just have to use our noggin a little bit. So what I'm really looking for, where cosine x minus sine x equals 0, that's equivalent to saying I'm interested where cosine x equals sine x. And you totally know where that exists on the unit circle, right? Because if I look at the unit circle, that would be where I get these square root of 2 over 2's or negative square root of 2 over 2's. So those are the two places where sine and cosine are equal. So we can leverage the unit circle to help us figure this out. So even though we couldn't get this in terms of one trig function, we could still figure it out. So it was okay. So those are the degree measures where cosine of x and sine of x are equal. And so then I just want to focus on the patterns. So these are 180 degrees apart, as are these. So when I come up with my solution set, I get 90 plus 180 degrees times n, and 45 degrees plus 180 degrees times n. Okay, and so that brings us to the end. So hopefully this was helpful. So this isn't going to prepare you for every single trick that comes up in a trig equation. This is just a good starting place. You'll probably find some more as you're going through your homework. Don't be frustrated. Just when that happens, just say, oh, okay, that's a new trick. I didn't know that was something that I could do. Just note it, remember it, and then move on. And otherwise, thanks for watching, guys. I'll catch you in another video.